Hello. For today, we're going to find the least squares solution of ax equals b and then find the error. The first matrix is a 6 by 4 labeled A, as seen here. And then our second matrix is a 6 by 1 labeled B, also seen here. So for the first step, the first thing we want to do is set up the least squares equation. The least squares solution is obtained by solving the normal equation A transpose AX is equal to A transpose B, as you see here, the normal equation. And also the equation AX minus B in the little lines squared is the equation that minimizes the squared error. So those two formulas will be useful later on throughout this problem. The second step of the solution is we want to compute the matrices A transpose A and A transpose B in order to help solve that normal equation that I mentioned earlier. So for the first step, we're going to compute A transpose, which is just the transpose of our original matrix A, which is now a 4 by 6 matrix. The second step of this is we're going to multiply A transpose by A in order to get the A transpose A matrix, which is going to be a square since it's a 4 by 6 multiplied by a 6 by 4 matrix. As you see here, we multiplied it out and we got our new square matrix, which is A transpose A. The third step of this is to multiply A transpose by B in order to calculate A transpose B, which is going to be the column vector that we need for the normal equation mentioned earlier. When we multiply it out, it's a 4 by 6 matrix by a 6 by 1 matrix, so we get a 4 by 1 column vector, as seen here. The third step of the solution is we want to now solve that normal equation that I mentioned. So we're going to write out the augmented matrix for the system, which is once again A transpose A times X equal to A transpose B. As you see, we've written it out here. We just augmented it. And then when you use row reduction techniques, such as the Gaussian elimination, we row reduce it in order to be able to then solve for X. One thing about this step in the problem is we want to avoid computing A transpose A inverse explicitly, as it's not necessary in order for us to solve this system. You never want to solve the inverse. You'd rather do it with these steps that I'm about to mention. The fourth step of the solution is we want to express the general solution. So using our augmented matrix that has been row reduced, we're going to get x1 plus x4 is equal to 3, which then you bring the x4 over. So x1 is now 3 minus x4. And you do the same thing for each of the rows of the matrix. So we have x2 minus x4 equals -5. So then x2 is equal to -5 minus or plus x4. X3 minus x4 is equal to -2. So therefore x3 is equal to -2 plus x4. And then the last row of the matrix, the augmented matrix that has been row reduced, is all zeros. So therefore x4 is going to be a free variable. So because x4 is the free variable, we express all of the other x terms in relation to x4. And then when we combine the solutions of all the other variables together, we get the general form of the solution, which is A hat is equal to the matrix 3, -5, -2, 0, plus x4, which is the positive or negative sign on the x4 terms in the general solution. So obviously for the x1 one, it's negative, x2 it's positive, x3 it's positive, and then x4 is just 1. If x4 is equal to 0 in for one solution, then x hat would be 3, -5, 2, and then 0, which is the first part of that general solution. Next, we want to compute the error of the estimate. So in order to compute that estimated vector, we're going to have b hat is equal to a x hat. So we want to use the original matrix A from up above, and then our solution that we just got x hat, and then when you multiply those two together, it's a 6 by 4 multiplied by a 4 by 1. So we're going to get a 6 by 1 column vector. And then when we do that, that would be our new b hat, which we get negative 2, 1, 1, 3, 3. After doing that, we want to calculate the residual vector, which is b minus b hat. So we take our original b, negative 3, negative 1, 0, 2, 5, 1, and we subtract off the b hat that we just solved for, which is negative 2, 1, 1, 3, 3. And then we get our residual vector, which represents the difference between the original and the estimated vector of negative 1, 1, negative 1, 1, 2, negative 2. Next step is to find the norm of the residual vector, which is error equaling the distance of b minus b hat, which is the column vector we just solved for. So basically, you take every single term of that column vector, you square it, and then you add them all up, and then you take the square root of that. So as you see here, we get the error to be equal to the square root of 12, or also 2 root 3, which is the norm of the residual vector. Now, when we want to interpret this error, we would say that this value represents the magnitude of the difference between the original vector b and the projection onto the column space of A. That's how we interpret the negative 12 in this scenario. A few important notes to go over on this first question is we should never use the inverse of A or the inverse of A transpose A in order to solve the problem. It's easier and more efficient to just use the direct row reduction methods as seen with the augmented matrix that we row reduced down in order to get our general least squares solution. And obviously, always double check your answers because if you mess up either the the A transpose A or the A transpose B, it will mess up uh your solution early on. So just make sure you get all those uh matrix multiplication problems down, make sure they're all correct before you continue.